In this lesson, we're going to focus on how do I use limits to determine the continuity of a function. So it's probably jumping out at you that you're going to need to understand what the concept of a limit is and what does it mean to be continuous. So a continuous function is a function that has no breaks, holes, or gaps in it. I think if I took my pencil tip and I traced along this curve, I can make one smooth, continuous motion with my pencil along this graph. Let's talk for a minute about the idea of a limit. And a limit is the concept of approaching a value without necessarily ever reaching it. For instance, if we wondered what this graph is doing at x equals 2. Okay, so as we approach 2 on the left side, we probably would assume, well, it looks like it's approaching the y value of 4. And as I move from the right side towards 2, it also appears that it's approaching 4. But do we ever really know? Well, but if we move that window away, we really have 3 scenarios for what could actually be happening. Well, we could have what we expected is that there's just a point and that curve continues here, that it really does have a point here at the 0.24, or perhaps there's a hole right there, but it's still approaching 4 on either side of 2. Or perhaps we have a hole that jumps down here and the point's way down here, but the limit here is still approaching 4. So all 3 of these scenarios have the same limit because they are all approaching the y value of 4 as they approach 2, the x value of 2 on either side. So let's look at how we write a limit. This notation here on the left is how we write a limit. It's read as the limit of f of x as x approaches c, which is some number, is equal to L. Pause, read that again, and practice saying it. So in the scenario with the window, in all 3 cases, the limit of f of x as x approaches 2 is equal to 4. Now, not all functions are continuous. As a matter of fact, we have quite a few discontinuous functions, and we classify the type of discontinuity that we see. So the first is removable discontinuity. So I trace my pencil along this line, there's a hole right here. Okay, so removable discontinuity can be plugged with a single point. Okay? There are 2 types of non-removable discontinuity. We call it jump discontinuity and infinite discontinuity. So jump, it's kind of like you're tracing from left to right this graph, and then your pencil tip jumps all the way up here and continues, infinitely to the right. Notice it is still a function because I have an open circle here and a closed circle here. So there's a gap. That's what we call jump discontinuity. And it can't be plugged with a single point. Infinite discontinuity is when we have a gap at the c value, but the graph, the y value is like shooting off towards negative infinity. Over here, it's shooting up towards positive infinity. It's possible that they'll both go infinitely upward because there's what's known as, we'll talk later, as a vertical asymptote right here. Might as well mention it right now. Vertical asymptote is this line like this that's kind of understood to be there. We'll talk about algebraically why it's created later. But the graph approaches it and gets closer and closer and closer infinitely to it, but never ever touches or crosses it, okay? So this has infinite discontinuity. What I was saying is you'll see some where it might look, you'll have something like this where they're both going towards positive infinity. That's a possibility where you have a vertical asymptote. So of course we have ways of proving functions to be continuous in higher order math. There's something known as the continuity test. So there's 3 parts to this. In order to prove that a function is continuous at x equals c, you have to prove these following 3 conditions. First of all, f of x is defined at c. What's that mean? It means that if you plug in a number into your function, it exists. You get an actual value. So you check that. Then you check that the function approaches the same value from either side of that number, of that constant. In other words, we're saying that the limit exists. And the third thing we do is we check to see if condition 1 is equal to condition 2, all right? If you get the same value, we've proven that it's a continuous function. This is easiest to understand with an example. So first, to see if it's continuous at x equals 2, just plug 2 into your function. To see that the limit of f of x exists as x approaches 2, I'm going to go to the graphing calculator. So to check the limit as f approaches 2, I like to look at the graph, type it. Zoom 6 will take you to the standard viewing window, and I just kind of check if I see any discontinuity. And I want to check out the limit as x approaches 2. So it appears to be approaching the same value of 9. To really get a sense of it, I'm going to look at my table, second graph, and my table's counting by ones currently. So I want to go to something much smaller so I can see it approach. I'm going to start at 2, and I'm going to change this to see every thousandth. And now I'm going to just scroll up a little bit and look at what I can see. I see as I'm moving from the left side of 2, it's getting closer and closer to 9, and on the right side of 2, it's also approaching 9. So I can numerically see that the limit of f of x as x approaches 2 is 9. So the limit of f of x as x approaches 2 is equal to 9. So the third part of the continuity test is just saying, does part 1 equal part 2? And it does. We can say that the limit of f of x as x approaches 2 is equal to the same value as f of 2. So it is continuous. Therefore, it's continuous at x equals 2. So in this one, you're given a piecewise function. Let's go just through another example. So I'm testing at x equals -3. So when I plug in, it's going into this part of the function. So it would be 2 minus -3, which is equal to 5. Second part of the continuity test, I'm going to go to the graphing calculator. And since it's piecewise, I'm going to plug in each part first. So on the left side of -3, I'm going to use this bottom linear portion. So on the left side, as I look at my XY table, I see 5.003, 5.002, 5.001, and then it would be 5. Now on the right side, I'm going to use this portion of the function. So when I switch this out on my graphing calculator, I get -11, -10.99, -10.98. So I see that it's approaching different values as I move this direction. Here it's this way. On the left side, it's approaching 5. On the right side, it's getting close to -11. Different values. So I'm actually going to say that my limit does not exist, because it must approach the same value. So I'm just going to write that by saying DNE for does not exist. So I already know that this is discontinuous. Now, what type of discontinuity do we have? Well, you should be able to tell by looking at this right here that it's jumping. It's got this jump between 5 and -11 in the y values. So jump discontinuity. So I have another example here where we're trying to see if it's continuous, and then we're going to identify the type of discontinuity if it is discontinuous. So I start, again, my continuity test is listed at the top of the screen. I'm checking f of 1. When I plug this in, I have 1 over 1 minus 1, which is 1 divided by 0, which we know is undefined. Can't do this in math. All right, so I definitely have a discontinuous function, but let's check out our XY table to identify what type I have. So here's what I'm seeing on my calculator screen. On the left side, look at this. As I get closer to 1, on the left side, it's getting much greater. Whereas on the right side, as I get closer to 1, it's getting smaller and smaller. So one's going upward towards positive infinity and the other side is going downward towards negative infinity, which tells me that I have infinite discontinuity. I didn't quite finish my statement though about the limit here. So the limit of f of x as x approaches 1 also does not exist because it's approaching different values on either side. All right, third one, I have polynomial function, f of -2. Check the first part of the continuity test. I plug that into my function. -2 cubed minus 2 times -3 is going to be what? -8 plus 4, it equals -4. Okay, so first part satisfied. Second part, I need to check the limit at x equals -2. The limit of f of x as x approaches -2. So again, I'm going to go to my graphing calculator. So here's a screenshot so you can see what I'm looking at on my calculator. As I approach -2 on the x on the left, it appears to be approaching -4. As I approach -2 on the right side with my x values, my y values also seem to be approaching -4. So now for the third part, are these two values equal what you see in 1 and 2? The limit of f of x as x approaches -2 is equal to, yes, we know it's -4, but we want to show that it's equal to the same value as f of -2. So this is continuous at x equals 2, or I'm sorry, x equals -2. This final one, you pause the video, see if you can check it, and determine the type of discontinuity, or tell me if it's continuous. So I plug in 1, and I get a divide by 0 error, so it's undefined. So secondly, I look at my table, and as I'm approaching 1 on the left, I appear to be approaching 1 on the right. It's getting really close to it. And then on the left, I would say I'm also approaching 1. So even though it's undefined right here at 1, the limit does exist. The limit of f of x as x approaches 1 this time is equal to 1 as well. Okay, so what kind of discontinuity do I have? Well, couldn't I just plug this hole right here? If there were a 1 right here, wouldn't I have a continuous function? So this is removable discontinuity. You should now be able to apply the 3 parts of the continuity test, and you should be able to identify your types of discontinuity, and you should be able to explain a limit.